All right, so let's talk about 2.3, number 29. I remember the good old days when this wasn't applicable to our everyday lives. This was just an abstract concern. All right, so an epidemic spreads through a population at a rate proportional to the product of the number of people infected and the number of people susceptible but not yet infected. Okay, why would that be the case? Basically, they're saying the d let's see, di dt is some constant k we don't know times I times s, where s is the number of susceptible. Why would this be the case? Why would it be just a product between these?
Because the more people you have infected, the faster the infection's going to spread. And the more susceptible people you have, the more targets you have. So as the number of susceptible people gets smaller, the rate decreases. And as the number of infected people gets smaller, the rate also decreases. So it's
Yeah,
kind of codependent.
certainly this thing has those properties, but why is it a product in this case? Um, Basically, it amounts to the idea that in order for you to infect, right, if you are infected, in order for you to infect someone else, you have to encounter them, right? And so this product is the number of possible interactions. Does that make sense? Between an infected person and a susceptible person. Does that kind of follow? Like, I don't know where that interaction's occurring. This is really just kind of assuming that the population is relatively well mixed. But those interactions occur in places. Right now, they're occurring in grocery stores and Lowe's and at the, wherever the heck it is that you work, which is why schools are closed, because schools make these interactions happen all the time, right? So there's kind of there's several things that people are trying to crank on right now to try to get the pandemic under control. And those things are basically all three items in this equation, right? K is kind of the one, the number of interactions, and two, the likelihood that an interaction between an infected person and a susceptible person results in infection being transmitted, right? So we're trying to reduce the number of interactions by closing some schools or businesses or whatever. We're also trying to reduce the likelihood of transmission by asking people to stay 6 feet apart and wear masks and not, do all sorts of behaviors, right? We're trying to reduce the number of people who are infected through a number of ways, but I mean, one of those is that we're trying to get people not to go out when they might be infected. And then we're trying to reduce the number of susceptible people. How?
Vaccinations
Yeah,
and isolation.
trying to vaccinate everybody, basically. You guys kind of understand that whole thought process? This lecture used to be a lot more fun when it wasn't so interesting. All right. Therefore, yeah, okay, stuff. Uh, oh, yeah, I guess so. I wrote this equation, but I didn't take this part. Why don't I have that part?
Because you didn't account for the fact
Oh,
that whenever somebody gets infected, they get subtracted from the susceptible population.
yeah, it's really just their notation. So they're saying S denotes the total population of people who can get it, and I denoted S as the people who are susceptible, not yet infected. So I'll go with their notation. So we'll do this. This would essentially be everyone who's not naturally immune, right, or already vaccinated. And R is a positive constant. Okay, so they swapped K for R. I guess that seems reasonable. That's just notational. Okay, so they wrote this down. You guys with me that this is basically the statement that they made written in math? Okay, and so assuming that I of 0 is I naught, find I of t, and then show this thing. Okay. All right. So, what do I do with this?
I mean, I tried separating it but I kind of got nowhere with that.
Yeah, so I think maybe we want to think about how this could be separated. Do, I don't know, something with it. Okay. So let me think. Um, well, all right, let's think about what depends on t. So does S depend on t? The total population of susceptible people, right?
No.
Yeah, that's not changing with respect to time, at least in this kind of model, right? Do you guys see that is changing with respect to time in our current situation?
Yes.
Yeah, that's changing by something like a couple 100,000 people a day getting jabs, right? Okay, so in my case, this is a constant, right? This is a number. How about R?
That's a constant.
Yeah, that's also a constant in this case. Is that also a constant in our situation? Not really, actually. Right, the rate of infection, this kind of constant of proportionality is a function of a number of things. One is how much people are mixing. One is a consequence of how many people are wearing masks. One is a consequence of how good the masks that people are wearing are. So if you kind of think about this R as constant, that's fine for a first pass model. But in general, that number is also changing as a function of time. You guys see that? The goal, by the way, is to get the kind of the number of infections that an infected person causes below 1. Right? If we can get it so that everybody who's infected on average infects less than one person, then this will tend to die out and we can maybe get back to normal at some point. All right. At any rate, here, I have numbers in these spots, right? So I'm kind of looking at this thing and I'm thinking to myself, this looks like di dt is 3i7 minus I. So how would I separate something like this?
You could just multiply it out and integrate.
Yeah. Well, the i's need to go to the other side though, right? Because I don't know what the antiderivative of I is.
All right.
You guys see that? Because I'm integrating dt. So really, I just need the i's to one side and the t's to the other. Well, I haven't any t's in this. So I'm just going to shove all this stuff to the other side. You guys with me on that? So I'm going to take this thing. I'm going to multiply this whole thing.
Joe? Uh-oh.
Hope he didn't like lose power.
Oh.
I thought it was me for a second.
Well, same.
Same.
But, no, I mean, I saw you guys moving still, so. Starting to think his Zoom might have crashed.
Probably.
Yeah. Okay.
Oh, there he goes.
Jacob, you are now the host of the meeting.
Okay, so the power cycled. I don't remember what I was saying. Oh yeah, I have to multiply this crap to the other side. So I have 1 over I times S minus I di equals R dt. Something like that.
Works for me.
Okay, next thing's next. Well, I think I have to figure out how to integrate this thing on the left-hand side, right? So I have to do some kind of integrating. On the right, I'm pretty sure I have RT plus a constant.
Isn't the left kind of like Ethan's weird way of factoring out an I squared and then doing a U sub?
You could do that, yeah.
Yeah. I think, as you say, the left is partial fraction decomposition, and I don't remember what Ethan's weird trick for avoiding that was. Okay, so I'm just going to do partial fraction or Ethan, remind me of your trick. What's your trick?
It's you factor the I in, so you get SI minus I squared, and then you factor an I squared out, or you just factor an I out of it, so you get I squared times S over I minus 1 over I squared.
Hang on, what? So I do this.
Factor an I out.
Okay.
Or sorry, factor an I squared out.
Of the bottom?
Mm-hmm.
Oh, okay. So instead of I see. So I need to factor an I out of that thing?
Yeah. Mm-hmm.
So I should have I squared times S over I minus 1?
Yep. And then you could do U sub.
Okay, so then I let U be this thing?
Yep.
S over I minus 1, and then du is
Negative S over I squared.
okay.
And then your constant.
That's a di.
Mm-hmm.
Okay.
So you're missing a negative S, so you'd have to factor that out, to the front in your final integral.
Okay. Yep. In order to get this done, I need a minus S in here, so I need a 1 over minus S out there. This is a weird U substitution method. Bridget, are you?
I'm good. I'll just have to take some time with that.
Yeah, so this is kind of a weird method. I'd be really inclined to do it by partial fraction decomposition. So if I was doing partial fraction decomposition, I'd think, all right, so I've got 1 over I times S minus I. That's supposed to be some number A over I plus some number B over S minus.
And may I point out that when I first brought up this method for doing this, Joe's comment was, quote, "That's really fucked," unquote.
Yeah, I'm pretty sure I don't recommend this method.
Don't blame you.
Mental gymnastics, yeah.
Well, it works in a very special case that you have a bare variable times a linear function of that same variable. So it's like partial fraction decomposition that only works in one very special case. I don't think it's worth, but Ethan for some reason sees that thing, so whatever. I would do partial fraction decomposition here. So then out of this stuff, I'm going to get 1 is A times S minus I plus B times I. And then we could kind of figure out what we need. Well, it seems like I'm supposed to get 1 is AS minus AI plus BI. I'm pretty sure there aren't any I's over here, right? So that means that these two terms cancel. So I'm pretty sure that means A equals B. And then the other terms there are going to tell me that A is 1 over S. You guys with me on that? Okay, so all told here, however you do this, let's see. I'm going to do my partial fraction decomposition. So I'm going to have 1 over S times the integral of 1 over I plus 1 over S minus I di is RT plus C. I'm going to just call ick on Ethan's method. Okay, and then I can maybe get some stuff together here. How do you integrate these? It's the integral of 1 over I di.
Natural log of absolute value of I.
Okay. And then this other one is a little U substitution later. What did I do wrong there?
It's minus.
Yep. Oops. Damn it. That was not very helpful. Okay. And that's supposed to equal RT plus C. Are you with me on that?
Yep.
Okay, so a little bit of combining here. I'm going to multiply the 1 over S to the other side. So I'm going to get log of the absolute value of I minus the log of the absolute value of S minus I is SRT plus C. S times C is still C here because S is still a number. Everybody on board with that? Okay. Now I'm going to form a ratio here using a log rule. So I'm going to have the natural log of I over S minus I is SRT plus a constant. I'm going to exponentiate both sides. Get I over S minus I is E to the SRT times a constant, maybe A. Are you with me on that? Okay, then we still need to solve. So I'm going to multiply both sides by S minus I. I'm going to get I is SAE to the SRT minus AIE to the SRT. Pretty good with that. Then a little more algebra. This thing needs to go to the other side. So I'm going to have I times 1 plus AE to the SRT is going to equal SAE to the SRT here. Then maybe divide. Ultimately getting this, oops, that's not an I. That is supposed to be a 1 plus AE to the SRT. Oops, why am I writing T's? That's supposed to be an R. SRT, SRT. Okay. Everybody good with this?
Yeah, I see my problem. I was treating S as a variable when I should have been treating it as a constant.
Okay. Yeah, and in the end here, the other part of what they asked me to do, which is maybe the salient part, is assuming that I of 0 is something, find I of t. Okay, so I think I did that. This is I of t. I haven't plugged in the initial condition, but we could do that. It's here, right? You could solve for A out of this. Everybody with me on that? Okay, now the other question is what happens as t tends to infinity here? So as t tends to infinity, what do you get?
Well, you're gonna get infinity on the top because of
This
the
thing's
E,
going to be basically infinity, right?
and
so you're
so
gonna
is
have
the
like
bottom.
you're going to have like s times infinity over 1 plus infinity. You see that?
And you could kind of think about it that the infinities cancel.
Well, yeah, I would kind of think about it as adding 1 to infinity makes basically the same number, right?
Right. And since the two infinities grow at the same rate because they're the same function, they basically cancel.
Yeah, so if you want a heuristic way to do limits, you kind of think, okay, so if I plug in a really big number here, I'm going to have s times a big number over 1 plus my big number, right? 1 plus the big number is more or less the same as the big number. And then the ratio of the big number with itself is going to be 1. You guys see that?
Yeah.
So this is
if you wanted to do it the proper way, you'd have to go through like L'Hopital's rule a couple times and all that.
Yeah, I mean, you could L'Hopital this thing. The other way you could do it is you could multiply top and bottom by 1 over a e to the SRT. And then this piece would have a 1 over a e to the SRT, and so it would go to 0. So then you'd have s times 1 over something that goes to 0 plus 1. Either way, you get to s. You guys with me on that? What does that mean?
Means eventually all of the susceptible will get infected.
Yeah, and this is so this basically means that as time continues, everybody will get it eventually. And so there are a couple things about disease modeling that are worth mentioning here. One, if this was true, like if this model actually worked perfectly, the chickenpox wouldn't be a thing anymore. Why?
Because everybody would have got it at one point or another, so the entire population would now be immune or dead.
Yeah, so why isn't this true for chickenpox?
Because new people are introduced into the population so they can get susceptible.
Because new people are added to the population, right? And those people are susceptible. You guys see this? So this model has it's a little bit simplistic, right? Which is why it's not the be all and end all of epidemiological models, because it's just a little bit too simple. Because it doesn't allow for people to age into susceptibility, right? Because the susceptible number is a constant in this case. So if you wanted to do a better job, what do you need to incorporate?
Population growth.
Yeah, you need to incorporate the susceptible number as a function of time. Yeah. What's the downside of doing that?
Makes it a heck of a lot more complicated.
Uh-huh. Yeah, this is kind of the constant push and pull of mathematical modeling. Is like on the one hand, you want an accurate model, which means you need to incorporate a lot of things. On the other hand, you want a model that you can actually solve so that you can make predictions. And the more things you incorporate into the model, the more accurate it would be, but the harder it gets to solve. Does that thought process make sense? Eventually, you arrive at the idea of like, oh, okay, so what I'll do is I'll make the computer pretend that they're little people, and those little people, I'll program them to act like regular people, and then I'll track this disease by modeling all these people, right? The problem is that a model like that takes a long time to compute. And so you run into this, like, if I'm going to model the whole population, I'll really just make a miniature of the whole population. There was an applied mathematician who used to say that the best model of a cat is a cat, preferably the same cat.
I mean, it's a fair point.
Yeah, it kind of is a horrible thing because you're like, okay, so I want to make some predictions. Well, the best predictions available are for me to just duplicate the situation. But I can't duplicate individual human behavior. It's a little bit too random for that. So I have to settle for something, right? And the thing we usually try to settle for is some kind of middle ground between accurate results and computational complexity. And in the case of epidemiology, I think we're seeing that kind of agent-based approaches, where you think about all the little people separately, actually yield pretty decent results. It is a little bit hard to know what a human being does. And you can't just ask them. Why?
We lie.
Yeah, human beings are really good about lying about their behavior. They tend to overestimate the things that they view as positive. They tend to overestimate their participation in those things and underestimate their participation in things that are negative. So, like when you ask, what percentage of the time out in public do you wear your mask? Well, if they view mask wearing as positive, they'll vastly overestimate that number. And if they view it as negative, then they'll vastly underestimate that number. And then there's all sorts of other weird perverse effects, like sometimes if you tell people to do things, they'll do the exact opposite because they just don't believe you. And that's been a problem. Anything else on this kind of mathematical modeling idea?
No.
Okay. Cool.